Good morning and welcome to the class on digital signal processing. In the previous classes, I have explained you how to design the analog filters. Analog filters are designed using two techniques. One is Butterworth filter design and the second one is Chebyshev filter design. Next, we need to convert these analog filters designed to digital domain. In this class, I will explain you how to convert an analog filter into a digital filter. In literature, there are several techniques to convert an analog filter into digital filter. And most of the techniques are based on converting an analog filter into digital filter. Now, I will explain you the desirable properties of the conversion technique from analog filter to digital filter. Desirable properties of conversion technique. The first property is the J-ohm axis in the S-plane should map into the unit circle in the Z-plane. The first property states that in the S-plane, the J-ohm axis should map to unit circle in the Z-plane. Because of this mapping, there will be a one-to-one relationship between the analog frequency variable and digital frequency variable. The second property is the left half plane of the S-plane should map into the inside of the unit circle in the Z-plane. When in the S-plane, there are two planes. One is right half of the plane and the second one is left half of the S-plane. If the poles are considered in the left half of the S-plane and if we design a filter, then it will yield you a stable analog filter. So, we need to have a mapping which maps the entire left half of the S-plane into inside of the unit circle in the Z-plane. Because of this mapping, the stable analog filter will be converted to a stable digital filter. In the next, we will see the different mapping techniques. The conversion techniques are mapping of differentials, impulse invariant method, bilinear transformation, and matched Z transform. Now, we will study the mapping of differentials. Mapping of differentials is the simplest technique to convert an analog filter into digital. In this technique, the differential equation in the S-plane is approximated with difference equation in the Z-plane. So, in the S-plane, if we have a differential equation d of y of t by dt, we can approximate this one with a difference equation, and that difference equation is backward difference equation. So if we sample the y of t at t is equal to nt, then we can approximate this differentiation with the difference equation. So y of nt minus y of nt minus 1 by t. So this one is the backward difference equation. Now this is the S-plane differential equation approximated to a difference equation. Now the Laplace transform of dy of t by dt is equal to s into y of s. So if we have a system which has input y of t, and if the system has the transfer function yes, then the output will be s into y of s. That is nothing but the time domain is you are getting the differentiation. In the same lines, if we go for the digital one, approximate this one, then First, we will approximate that y of nt is equal to y of n. Then this difference equation now can be rewritten as y of n minus y of n minus 1 by t. And here this t is the sampling interval. Now, if we take the z transform of this difference equation, we will get y of z minus z power minus 1 y of z by t. Now, take the y of z common. So, 1 minus z power minus 1 by t times y of z. Now, this one, if we are implementing in the system form, then if the input is say y of n, and then if the system transfer function is 1 minus z power minus 1 by t, then you are going to get 1 minus z power minus 1 by t into y of z. This is nothing but the backward difference. The backward difference. Now, we will compare this system with this system. That is, this is the S-plane system and this is the Z-plane system. Now, both of them are implementing the differentiation. That is, we will map the differential term in the S-plane to the difference equation in the Z-plane. So, thereby, if these two are approximately equal, then these systems should be approximately equal. Therefore, the mapping will be S is equal to 1 minus z power minus 1 by t. That is, given h of s, that is, if we have the analog filter transfer function h of s, then if we want to have the digital prototype of this one, then h of z is equal to h of s at s is equal to 1 minus z power minus 1 by t. This one will give you the analog filter converted to the desired digital filter. This is the mapping of differentials, a simplest technique which will approximate the differentiation in the S-plane to the difference equation in the Z-plane. Now, we will convert a first order filter into its corresponding digital filter using mapping of differentials. The analog filter transfer function h of s is equal to 1 by s plus 2. This is a simple first order low pass filter. Now, if you want to have the h of z, the corresponding digital filter using the mapping of differentials, then h of z is equal to h of s at s is equal to 1 minus z power minus 1 by t. So, to convert an analog filter into digital filter, we need a specification of the sampling interval t. We will consider this sampling interval t to be 1 second. Then this analog filter, so h of s is equal to 1 by s plus 2. Now with this time interval or with this sampling interval, the corresponding h of z is equal to h of s at s is equal to 1 minus z power minus 1, and this is equal to 1 by 1 minus z power minus 1 plus 2, and if you simplify this one, it will be 1 by 3 minus z power minus 1. So this is equal to z by 3z minus 1. The analog filter transfer function is 1 by s plus 2 and the corresponding digital filter transfer function is z by 3z minus 1 using mapping of differentials. Using mapping of differentials. Thank you.